Welcome to the course Environmental Impact Assessment. Water is a necessary component to complete the EIA process. There are legislations, guidelines and standards for the purpose for evaluation. Water is also a supporting factor to many other EIA components, for example, biodiversity, soil and human health. The standards for water quality and geomorphological are usually set by governments and are regulated by governmental bodies and agencies. Mostly we see that in many countries, the most strict standards are set for drinking water, as we see by the WHO standard as well as CPCB standards. We also see standards for regulation of wastewater from domestic and industrial sources. Control can be also placed in the volume of discharge, as well as we see restrictions are often applied on the volume of water, extraction in specific periods of time, mostly in low flow periods, as well as flood standards. Specific flows may be required in a stream or a river to support aquatic fauna and flora, and one method for calculating the requisite flows is the in-stream flow incremental methodology. Other examples are also there, like Water Framework Directives WFD, where compliance assessment to determine if there is likely to be any deterioration of ecological status as a result of development activities based on hydromorphic condition. Hydromorphic conditions captures the interrelationship between flow regime and the channel parameter. Geomorphological baseline information is common in EIA process. We also see flood risk assessment to minimize the likelihood of new projects being subject to flooding and or increasing flooding anywhere else. We see that parallel assessment of these processes is desirable in EIA. We also note that the World Bank requires EIA of projects proposed for bank financing through its operational policies and environmental assessment source book. Specifically, policy 4.07 is concerned with water resource management. Bank requires study and management of flood control, potable water, sanitation facilities and water for productive activities in a manner that is economically viable, environmentally sustainable and socially equitable. Further, World Bank specifies pollution levels and control measures and emission levels acceptable to them. These criteria may vary from country to country. So focusing on water, we see that how important it is. So today we will look at methods used for EIA specific to water domain. Therefore, today's coverage will include definitions and concepts, where we'll cover water quantity. We'll look at the environmental flows, baseline flow, return period, water budget estimation methods. We'll look at catchment approach, parameter for calculating water budget. We'll also look at water quality, fluvial geomorphology, methods for scoping like checklist, source pathway receptor model. We'll also look at method for baseline assessment, as well as we'll look into impact prediction and evaluation from indirect sources and direct sources. We'll also look at different softwares which are available for the purpose. And finally, we'll look at the evaluation of impact significance. So accordingly, the expected learning outcomes is that you should be able to define and explain the concepts of what water quantity means. You should be able to define environmental flows, base flow, return period, and so on. And you should be able to define or conceptually explain what water quality means, what fluvial geomorphology means. You should be able to decide on methods for scoping. You should be able to tell, identify checklist, and also explain source pathway receptor model. You should be able to use method for baseline assessments, and you should be able to identify what kind of data you will require for that. You should be able to identify possible impact, prediction, and evaluation methods for both indirect sources as well as direct sources. You should be able to list various softwares which are available and choose among them. Finally, you should be able to also look at methods for evaluation of impact significance. For today's session, the key reference will be Chapter 2 on water from the book Method on Environmental and Social Impact Assessment, edited by Ricky Tharwell and Graham Wood. So let us begin with some of the key definitions and concepts. Starting with water quantity. When we look at water quantity, we check water balance or budget. Water balance or budget for any hydrological system is estimated to predict, to know, or take account for various flow pathways. How is water moving and storage components? Where is the water stored in the system? So we look at all these aspects when we do the water balance estimation. Several developmental activities, like what really affects that. We see that activities such as when the forest cover is removed for urban development, it affects the evapotranspiration. It also increases the runoff rate, reduces the infiltration, meaning impacts the groundwater recharge. It also causes a reduction in infiltration, can also worsen flooding and erosion risk. Flooding occurs where water courses do not have capacity to transfer the surplus water which is generated. There are numerous property at risk in many countries, and it also has potential impact on our health and river system. Another example we can talk about is construction of dams, which affects the flood pulse, meaning the periodic inundation and drought. When we drain wetlands and marshes for development purpose, there also we see impact, the runoff increases from the land. Furthermore, we see agriculture also increases the runoff. Likewise, we see when we transfer water for domestic purpose, the housing, the supply we get in our house, or irrigation purpose, the quantity changes. We also change the water balance through drawing water for industry and agriculture purpose, and we reduce the flow. This impacts the availability of water in the downstream of the river. Also impacts aquatic ecology and how sediment transport through the system. Even by discharging wastewater from treatment plant, we can change the quantity. So we add to the existing water. Now let us see environmental flow. Environmental flow are the quality, quantity, and timing of water flows required to maintain the components, functions, processes, and resilience of aquatic ecosystems, providing goods and services to people. And we see that this is increasing being recognized as an issue, and guidelines regarding environmental flows are being established around the world. We may also acquaint ourselves with the concept of base flow. Let's see what's base flow. There is a movement of water between the surface body and the groundwater, which is referred as base flow. How much the base flow contributes to the river flow varies significantly with the geology and topography of a catchment, and it varies with the seasons. We will also make ourselves aware of return period, the concept of return period, or recurrence interval. Return period is the most common way of showing the chances of the flow or rainfall event to reoccur. It is a statistical analysis based on measured historical data, like you can see gauged flows or weather station data. A return period, what it tells us the chances of the same flow of rain increasing in a year. For example, 2-year return period event has a 50% chance of being increasing in 1 year, whereas a 25-year return period event has a 4% chances in a year. We see that 100-year event is usually used for flood risk mapping. For the environmental assessment purpose, the proponents have to establish that the development which is being done, whatever they are proposing, will not increase the likelihood of a particular return period event and therefore will not increase flood risk to the properties downstream. So that they have to establish that. The return period flows can also be used for the purpose of channel designs and in low flow assessments. Now moving on to estimating the water budget. Water budgets are usually calculated for a period of time and are given in depth in meters. They can be presented as a volume by multiplying the depth by the surface area of the watershed. A commonly used method to estimate water budget is given by Thornthwaite and Mather, which is precipitation, subtracting surface runoff, subtracting groundwater flow, subtracting evapotranspiration, which gives the change in storage in a specified time period. We also see catchment approach. So, another approach we see for calculating, which is also called as drainage basin approach. In this approach, catchments are separated by a watershed boundary, which is a natural division line along the highest points of land. Precipitation, that is rain, snow and so on, falling into the area of the catchment eventually reaches the same river. There may be evaporation or infiltration during the movement. Catchment can be divided into subcatchments also along lines of elevations, and they may vary widely according to the size and surface water and groundwater it holds. So, there can be variations in that as well. How the water moves in a hydrological cycle would vary as per the time and location. So, how is water moving? It can be different for different locations. The way water moves can cause surplus water and also cause rise in water levels and may be causing potential flooding, or it may also lead to deficit of water, potentially leading to drought conditions. So, you see the implications. Let us see the parameters and the process of calculating the water budget, where and how we get data information, and we are looking at the available information here. Let us see the parameter and the process of calculating water budget and see what kind of information is required. First, we see precipitation. We see that the rain, snow, sleet or hail that falls to or condenses on the ground, which is referred as precipitation, is the main input to the hydrological cycle. Usually, precipitation data is used to evaluate long-term effects of projects for a normal year. Data as suggested should ideally be tabulated by month, possibly using that you can use Excel spreadsheet for the purpose. Another parameter we see is surface runoff. Surface runoff can be estimated from runoff curves. The curves were developed from combination of hydrologic soil grouping, land use, and class of treatment. Daily runoff values can be collected using a device such as a funnel-shaped runoff collector. For detailed assessment requiring more accurate results, hydrologic models can be used to estimate surface water runoff. We will see some of the softwares which are available for the purpose. Another parameter we see is groundwater flow. The distribution of hydraulic head, which is the mechanical energy state through an aquifer, dictates where groundwater will flow. So, the hydraulic head determines where and how the groundwater will flow. For unconfined aquifers, let's see what's unconfined aquifers. And unconfined aquifers are those where water seeps from the ground surface directly above the aquifer. For unconfined aquifer, the hydraulic head is the water table itself. Looking at another factor, evapotranspiration. Evapotranspiration is the combined loss of water vapor from the surface of plants through transpiration and the evaporation of moisture from the soil and other surface such as lakes, rivers and oceans. Based on the soil and plant types, amount of potential evapotranspiration is determined. So, you can estimate that. There are methods for estimating actual evapotranspiration inputs required for estimation. We see precipitation, temperature and latitude are key for the purpose. So, moving on, now let us look at the concept of water quality. Surface and groundwater quality is determined by assessing three classes of attributes. Surface and groundwater quality is determined by assessing three classes of attributes. First, the chemical attribute, the dissolved chemical solutes which originate from atmosphere, soil or weathering of bedrock. We need to understand that the water is never pure. Second, the physical properties. We see that natural waters vary in the amount of particulate material present in them. Rivers typically carry large quantities of particulates. We can also see the term here, bed load. Bed load is the riverbed particulates. These particulates range in size, such as they could be silts, coarse sand, gravels or even boulders. These bed load materials can move when flow of water exceeds a threshold limit. Flow of water depends on both channel slope and discharge. Third, the biological attributes. Biological water characteristics are used to describe the presence of microbiological organism and waterborne pathogens. Many of these can cause health issues for humans and animals. These can enter water bodies either naturally or through release of untreated or partially treated sewage. Pollution can also happen, and the pollution can happen from point source or non-point source. We see that what impact happens on the receiving water, so that just does not depend on the development activities itself, but also depends on the water quality. So, how is the receiving agent in the quality of that also affects the impact of the development activities. For example, you may think of pollutant being released in the flowing water like river compared to pollutant being disposed in the still water such as lakes. So, we see that many countries have set standards for each of these attributes. Now, moving on, let us try to understand the fluvial geomorphology. When we cover fluvial geomorphology, we refer to the process of water and sediment movement in river and their floodplains, together with the forms produced by those processes. The term can be applied to both natural environments and those altered by humans. In this, we study the sediment sources, the fluxes and the storage within river catchments, and the channels over short, medium and longer time scales. We also study the resultant channel and floodplain morphology in the process. This understanding is essential to do assessment and design of sustainable fluvial projects. We also find term hydromorphology that covers larger aspects of fluvial geomorphology and also emphasizes on impact assessment as well as mitigation. It is important to understand the concept of geomorphological threshold. Geomorphological threshold is a condition allowing landform stability, a dynamic equilibrium. This stability is an equilibrium which is attained among many factors playing a coordinated role. For example, a river flowing across the floodplain, it looks static. It is not static, but it is stable, all works in the harmony. There can be several external and internal controls that affect the geomorphology of a river channel or a floodplain. You may pay attention to the external controls and the internal control. There will be changes in these due to the proposed development. So, whatever you develop, these might change it. You can see that the external controls are like catchment form, drainage network, flora and fauna, land use, modification, management practice, geology. Likewise, you can see internal controls like stream gradients, mode of adjustment, cross-sectional morphology, bed and banks condition. We can also learn about simple geomorphological classification of channels based on cohesiveness. There are other classifications too. However, river types vary widely, and an impact on mitigation solution applicable in one geography, whatever we see here, may be totally inappropriate for the another. So, it has to be very much contextual. So, you can see the range of the types here, the cohesive and non-cohesive. You can see the bedrock channels, silt day channels and so on. We may note that geomorphology is a specialist discipline, typically requiring specialist consultant to undertake during EIA. So, the consultant would take care of all the details and be able to give inputs on this process. Moving on, we will see the first stage of EIA process, scoping, while undertaking assessment underwater. We may recollect that scoping stage involves determining the types of activities likely to be involved in development, from construction through operation to decommissioning of the project if it is relevant, the duration of each of these stages and any alternatives considered. It is very important that we have a very clear understanding of how the proposed project will be operated given the local conditions. And all of these is required at this stage for early identification of potential impact, and it will be based on the professional judgments informed through the qualitative resource from the references you have. Here we see a checklist method used to determine the scope of assessment for dam project in Pakistan. We have now developed considerable understanding of impact of dam development during operational as well as construction phases. Water related impact of dam operations are usually very extensive, ranging from water quantity, quality and fluvial geomorphological study. So, you can see the checklist here. We also find scoping checklists for potential water related operational impact with particular reference to dam schemes. Checklists are simple methods used in many stages of EIA, so we are just looking at this particular stage. The checklist provides different issues such as surface water hydrology, river hydrology, surface water quality, erosions and sedimentation, geomorphology, aquatic ecosystems, and it provides sources of impact such as storage reservoir, flow diversion, so whatever you do in the dam, standing water which will be there, accumulation of sedimentation, changes, accumulation of sediments, changes in hydrology, and it also provides the potential impacts such as change in habitat and biota, dewatering, altering the fish species, potential changes in erosion pattern. The checklist is provided to you in the reading. We also see an alternative or complementary approach to checklist. So, you see this method, you have source pathway receptor model. The source for any effect is usually the specific development activity, and the pathway which we see here is the mechanism by which the source can affect a receptor, such as via hydraulic effects, and the receptor may include, it could be anybody, it could be physical, human, flora or fauna. A water course can then be considered as a pathway and as a receptor as well. Potential physical effects to the water environment from development may include river channel modification. So, the river channel can get modified from the activities like dredging, navigation, maintenance, elimination of freshwater lakes by the development, building a new dam which leads to loss of water body and downstream impacts on water and sediment discharge. We can also see discontinuance of dam or weir with potential to cause erosion and lead to sediments being released downstream. Potential water quantity effects include like replacement of natural vegetation. We might get more impermeable paved areas, and we can the effects could include man-made drainage system leading to decreased infiltration to groundwater and so on. Further, we also see abstraction from rivers which can cause reduced flow leading to deposition of fine silt, and in some cases channel narrowing. A new development which can increase the burden on the water supply and increase the volume of waste water as well. We also see potential water quality effects include artificial discharge, pollutants from new road surface, artificial cooling water discharge to environment from a power station leading to thermal changes. We also see potential geomorphological effects include increased channel erosion in streamline, changes to erosions and sedimentation pattern, changes to flows below an urban area or dam affecting the morphology of a channel, in-channel mining leading to localized erosion upstream and in tributary channels, diffuse point sources of fine sediments entering the channels from adjacent farmland and so on. Moving on to the next stage of assessments, which is baseline assessment. This particular stage involves describing existing baseline condition for water quantity, water quality and fluvial geomorphology for the area potentially impacted by a project. Typically, different data collection standards apply to different countries. So, in whichever country you are and practicing or preparing EIA. And professional judgment is key to this, and again you have to use expert consultants, which is often recommended. Collection of field data for hydrological parameter can be very difficult, and it can be time consuming as well, and it requires sampling over extended period of time. Resources and time constraint would also determine what method you use. Water quantity assessment require both desktop and field study. Desktop study will involve catchment boundary area and drainage pattern and information on geomorphology such as slopes, geology, soil and land use, which can be determined from the base maps, geological and soil survey maps. We also see use of digital terrain models. You can also procure existing flow records or estimation through use of rainfall runoff models. The limits of river floodplain may be already there based on the topography and hydraulic modeling. In this case, for quantity, field study involves temporary stream gauging to determine flow regime for high flows and low flows. It's usually needed, but this can be very expensive. So, mostly the secondary data is used for the purpose. If an assessment is needed of a length of river, this is normally divided into reaches, sections of fairly uniform morphometry and flows. Detailed survey data to input to hydraulic model, all these is done through the field survey. Further, we see for water quality, in this through the desktop study, use of existing information, if it is available is taken. Routine monitoring may be available for such purpose. So, that can be taken, the pollution level in the water, those readings can be taken here. For this, the field survey would include river chemistry. However, that's very expensive, and given the cost and time, it has limited value, so it can be taken from the secondary data. And then biological or fishery surveys are considered to be more valuable because they give a reliable indication of the long-term health of the water environment. Most groups of the freshwater organisms have been used as indicators of given pollutants. Now, looking at fluvial geomorphology, the desktop study would involve channel change over time, and which is determined from historic and contemporary maps and aerial photographs using GIS overlay, if that's possible. Desktop study would also be comprising of survey information, including geologic and topographic maps. We also see use of topographical information and digital elevation models to calculate stream power. The field study in this particular case would involve stream reconnaissance survey to collect information on channel size, survey of the channel to obtain accurate slope and bankful characteristics, and to record geomorphological features. Sediment analysis might also help, increasing the use of unmanned aerial vehicle technology like drones and etc. can also be used here. Moving to the next stage of impact prediction and evaluation, we see potential direct impact on water environment arising from different development activities. And you may note that local data and information is key for the purpose, and also the expert judgment is required to contextualize your studies. For example, the sources for indirect could be river engineering manipulations such as widening of the river, deepening or realigning and so on, embanking and bank protection. So, these could be the source of impact. Other direct source example could include clearing bank vegetation, fluvial dredging and deposition of dredging, diversion, culverting and so on. And then the potential impact would include loss of wildlife habitat and visual amenity value, damage to channel morphology, decreased supply in donor area, direct loss of open channel length and so on. So, we see likewise the development on river floodplain is another direct source, and it would also have several impacts. like increased flood risk upstream and downstream, reduced groundwater recharge, and river base flows. Other direct sources include reservoir and dam on stream, dams, above dam siltation. The impacts include loss of river section, changes in the flow regime. Another one we see mostly in the urban planning domain, it's the drainage schemes, possibly involving channelization for withdrawing water, sewage treatment work, and river crossing bridges, pipelines, and cables. So, this also has possible impact of increasing soil drought risk, oxidation of organic soils, water table lowering, wetlands, loss of wetlands. Now, we can see indirect source of impact on water. So, we see that roads can also bring changes. Likewise, we see urban and commercial development can also bring changes, industrial development, as well as we see mineral extraction, landfill, forestry and deforestation, and intensive agriculture. We see that impact prediction can be qualitative, so typically informed through professional judgment. It can be assessed by uses of checklists, matrix, flowcharts, and network analysis, but these tools do not assess the nature, magnitude, or significance of the impact. There are more complex mathematical modeling which can be used, however, they require professional input, and also the data which is invested is of key importance. Numerous models have been developed for simulating and predicting changes in hydrological system. Reviews are provided in many hydrological texts. Physical models are also sometimes used, but most modeling involves mathematical and statistical analysis of input data. We will run through the list of software available on public domain. The use of model has limitations, especially in relation to the time and resources restrictions common in environmental impact assessment. Some software is expensive. Most model needs expert input. So, we see Hydrological Engineering Center hydraulic modeling system, which is available for hydrologic watershed model, and so on. We see the entire list here. We can also see WinFab and all these softwares which are provided for all the purpose from different countries, and most of them are available in the public domain. So, we see the evaluation of impact significance. EIA practitioners are familiar with the combining the magnitude of impact with the value of an individual receptor to derive levels of significance. So, depending on the receptor, how significant is the impact. So, that is evaluated here. The matrix will need to be used, and it provides the overall assessment in line with the local circumstances. We will see the examples of criteria for assessing the magnitude of impact on water environment. No doubt different criteria will be relevant for different projects, but we are looking at the broad approach. So, we look like how the project will the activity would have major impact, adverse or beneficial, or moderate adverse or beneficial impact, and then minor adverse or beneficial impact, or it will have a negligible impact depending on the kind of results we get in the domain. The list is provided to you. Likewise, we also look at the sensitivity of the receptor. So, how sensitive is the receptor? Very high, the sensitivity is very high, or the sensitivity is just high. So, according to that, we decide what kind of actions have to be taken here. So, we see the parameters used for evaluating the sensitivity of the receiving environment. Summarizing, today we saw the definitions and concepts. We also looked at the water quantity, we looked at the concept of water quality, and also looked at the fluid geomorphology. So we also looked at the methods for scoping like checklist, source pathway, receptor model. We looked at the baseline assessment, impact prediction and evaluation. We looked at the list of softwares which are available, and then we looked at the evaluation of impact significance. So that's all for today. These were the references used. And these are the suggested watch and read because our coverage is very limited. So you can read more if you're interested and explore further. Please feel free to ask questions. Let us know about any concerns you have. To share your opinions, experiences, and suggestions. Looking forward to interacting and co-learning with you while exploring AIA. So that's all for today. Thank you.